Hello and welcome to this lecture. We will consider a slightly more complicated problem, that of a piston loaded by a spring, a linear spring, and the piston is charged by means of an air supply line. So, the air supply line obviously has a higher pressure, and then you open the valve is opened, and when the valve is opened, air at a higher pressure rushes into the piston. So, this P line and this P inner. So, P line is greater than P inner, and then it starts to move the piston, but because it is spring loaded, the moment you start moving the piston, it encounters a larger force, and thus the P inner, because also the volume is increasing. So, there will be a complicated relationship between the actual pressure, but as more and more air flows in, it has to flow in against a higher P inner. So, it has to do it against a higher pressure, and then the valve is closed, and then what happens? That is the question. So, the spring constant is given as 80 kilonewton per meter, and the initial volume is given as 1 liter. Let us call this as V0, it is given as 1 liter. Now, it is given that after opening the valve, the piston rises only when the cylinder pressure is 150 kPa. So, when piston moves, there has to be first enough pressure developed inside this particular chamber, and that pressure I will call it as P0, and that is equal to 150 kilopascal. After the closure of the valve, the volume V1 is given as 1.5 liter. It is given that the T is 80 degrees Celsius. What is the mass of air inside the cylinder? So, when the pressure is acting on the piston rises up, the final volume is given, the final pressure is not given, and the final temperature is given. Okay. But we do not know what the mass is, that is why we do not know what the specific volume is. So, total volume is not an indication of the specific volume. I do not know what the mass is, I cannot find out the specific, and total volume is neither a intensive property which I can use as an independent parameter. I cannot use total volume, I need the specific volume. So, that is why I need the mass of air, but I do not have the mass of air. So, but maybe you see the problem and you think, yes, it is given that it expands to this volume. So, maybe with that and the fact that the spring constant is given, I can find the pressure, and if the temperature and pressure are known, maybe I can find the specific volume, and with the specific volume and total volume, I can then find out the mass. Okay. This is how we should proceed. Logically, you have been only given the total volume, that is why you cannot proceed, you need to find out the specific volume and do it. But how can we relate the final pressure and the initial pressure with the spring constant? So, let us look at the equilibrium of the piston. So, because of the spring, apart from the atmospheric pressure, look, this cylinder is open to the atmosphere. Okay. Because it is open to the atmosphere, we can then write down the following facts. It is P atmosphere and K delta x apart from the mass of the piston. So, when piston just moves, we choose it as the reference point for the spring. So, we say P lower is equal to P atmosphere plus P piston. See, mass of pistons times G by A of piston is the pressure due to this. So, obviously P low into area is the force, P atmosphere into area is the force, and obviously this into area is the force, and K delta x is the force. So, from equilibrium, because the areas are equal, we know that P lower is equal to P atmosphere plus P piston is the equilibrium at the moment just when the piston starts to rise. So, P 0 is equal to 150 corresponds to the point where there is no pressure acting on, so there is no displacement. So, at this threshold the piston starts to move. At this threshold the piston starts to move. Now, once it starts to move, this K delta x will start accumulating. Therefore, we have P lower is equal to P 0, or rather let us write it down in this manner. P lower is equal to P lower into area is the force is equal to P atmosphere multiplied by the area plus P piston multiplied by the area plus K delta x. This is what you have, static equilibrium. Actually, during this process, we assume that the process is going on in a quasi-equilibrium manner, and thus we can write this down. We can write down the static equation. Because the process is in static equilibrium, there is no acceleration of the piston. Oops. So, let us rearrange this. Let us rearrange this. So, P lower is equal to P atmosphere plus P piston plus K delta x by A. Now, we have already seen that P atmosphere plus P piston was the threshold when it just starts to move. Okay. So, that is equal to P lower. So, that P lower for this particular state was equal to P naught. So, P naught, this two term become P naught, because P atmosphere plus P piston when it just starts to move is P naught, and we set that as a reference state for the spring. So, this becomes P naught plus K delta x by A is nothing but P naught plus K delta x into A by A square is nothing but P naught plus K delta V by A square. So, the final pressure or the pressure inside the chamber, which is equal to the P lower, is equal to the P naught when the piston just starts to move plus whatever change in volume you may accrue times K by A square. So, let us start crunching in the values. So, K is 80. So, this is in kilo Newton per meter. We need the kilo, I mean we do not get rid of the kilo, we do not multiply it by 1000 because we will use the kilo Newton to convert it directly into kilopascal. Otherwise, you have to multiply by 1e minus 3 to make a pascal into a kilopascal. We do not bother about that. We will see how it checks out. So, P 0 is 150 and what else is given? Delta V is given as 1.5 liter minus 1 liter. See, final volume is 1.5 liter, initial volume is 1 liter multiplied by the area of the piston. Oh, sorry. So, this multiplied by 1e minus 3. We have converted liter to meter cube through this step. Okay. The final temperature is given as 80 degree Celsius, and thus we need to know what P1 is. So, we have already seen through our calculation, through the logic, that P1, which is the P in the final state, is equal to P naught plus K delta V by A square. So, we need to know what A is. So, A equal to, what is the area? We know that the diameter of the piston is 10 centimeter, and thus the area is equal to 3.1415 multiplied by 0.1 square by 4. This is the area of the piston. Now, delta V by A square is in standard SI units. K is in kilonewton per meter. So, whatever this quantity will be is in kilopascal. P naught we have already written down in kilopascal, and thus this is consistent. So, we do not need any conversion going on. So, this is kilopascal already. So, thus let us see what the final pressure is. So, the final pressure is 798.5 kilopascal. Okay. So, because of this, what is the total mass? So, the specific volume, so let us write down directly. So, the mass is equal to the final volume, which is 1.5 liter, 1.5 liter divided by volume of air at T equal to T1, P equal to P1. And thus we obtain the mass as 0.01182. Now, we recall that air under normal operating conditions, when it does not liquefy and so on, does behave as a pure substance, and thus even to find out the properties of air, you can make do with just two independent properties. Okay. So, this is what the idea is. This was the volume. So, this we have just used the fact that mass is equal to volume by specific volume. This is the formula that we have used. The area is known. So, the crux of the problem was to find out how to find out the final pressure. And the crux was also in the fact that we cannot find the final mass directly with just the total volume. Total volume is not a intensive property, and thus we cannot use it in our calculation. We needed to find the pressure and the temperature. These are our independent quantities with which we were able to find out the specific volume, and after finding out the specific volume, we use the fact that the total volume divided by specific volume gives you the total mass, and this is how you find the total mass of the system. And the static equilibrium idea was used, where we say that the piston is in quasi equilibrium. Because of that quasi equilibrium, you can apply a static equation, a static balance, and then we saw that the pressure at which the thing is lifted is P chamber, if I may, is equal to P naught plus K delta x by A. So, when delta x is 0, when there is no movement of the piston, then P in the chamber becomes equal to P naught. This is the pressure at which just the piston starts to move, as seen from the problem. So, this is equal to 150 kPa from the problem. And because of this air supply line, we were able to achieve a much higher pressure. The much higher pressure was approximately 800 kilopascal. We went from 150 kilopascal to 800 kilopascal. Okay. We do not know what the pressure in the line is, but we have to assume that it is larger than 800 kilopascal. P line is not given in the problem. So, we know from our idea that if the final pressure is 798.5 kPa, the line pressure has to be at least larger than 798.5 kPa. So, maybe it is something like 1 megapascal or something, who knows, does not matter. So, initial whatever pressure it was, suppose the pressure was initially, let us try to, let us go beyond this and try to see what actually can happen. Let us draw pressure versus volume. So, like this. So, initially, okay, so this is air, so we cannot draw this saturated dome. So, this is air, okay, pressure versus volume. We are, maybe this is 150 kPa, and suppose you start somewhere over here, and then you open the supply line valve. You have opened the supply line valve, and you are at some lower pressure, maybe 50 kilopascal. So, up until the point, so what is this volume going to be? So, this is total volume. So, this volume is the initial volume. The initial volume is 1 liter, because okay. So, this is 1 liter. So, then you start letting air come in. The volume does not change, but the pressure changes. The volume does not change because in order to have a change in volume, you need the piston to actually move, but the piston is held by a spring, and the piston will not allow, the spring will not allow the piston to move until you reach a pressure of 150 kPa. So, this is how the process will proceed. The pressure increases up until it reaches 150. The volume is still 1 liter. So, this is A, this is B. Now, once it hits 1 liter, how does the pressure increase? The pressure increases linearly in volume. So, it increases linearly in volume. Up until the point, this is 1.5 liter, and this corresponds to approximately 800 kPa. So, this is how the process goes. You have released the valve, the pressure reaches 150 kPa, only after which the piston starts to move. So, here piston starts to move. Only when the piston starts to move, you have an increase in volume, and an increase in volume leads to a linear rise in pressure through this static equation. We have already seen from the static equation, this is how it varies, and thus it leads to an increase in pressure. So, this is how the process line looks. We will not do it in EES, it is trivial to show it. So, this is how we were able to find the mass. The logic was very clear. So, when you practice problems of this kind, please try to rationalize the problem before jumping into the problem. It helps in having a very nice flow to the program as well. If you do not rationalize things, the program will not have a flow. It is you who are doing the work and not the computer. The computer is there to give you whatever you are asking it to give. The computer does not solve anything directly. For example, I cannot just give a schematic and ask the computer, okay, solve this. It is not an AI, it is a human intelligence thing. You have to tell, okay, these are the equations, these properties have to be obtained using these independent parameters, and then give me this quantity, and thus this is how you should proceed. You should take it in this sense. So, next time I will meet you with more problems and we will discuss something else. I will see you next time. Bye bye.